Okay, let's start our lecture. So at the end of the lecture on Wednesday, we talk about the principle of a complex power balance. So we start with the calculation of a complex power using the voltage and current phasor. So if we apply this formula to each branch in the circuit, we assume that the three parallel branches are all loads. So we apply each of them, so which will be equal to the total complex power sent from the source, which can be easily proved. For this case, we can utilize Kirchhoff current law. But if you have a more complex circuit, you can apply the Kirchhoff voltage law as well. So finally, we'll have the balance. So the interpretation of this complex power balance law could be from different ways. The first one is if we know which element in the circuit really behave as a source, we just put such element on the left-hand side. And when we calculate the complex power, we need to utilize the voltage of that element and also the current leaving from the positive terminal. So to calculate complex power on the left-hand side, which we recognize as a source, we use the voltage and the current leaving from positive terminal. And for anything else, we just treat them as load, such as we need to utilize the current coming into the positive terminal, because here we define this as positive, so we also assume this terminal is higher than the other one. So we utilize the voltage multiplied by the conjugated current coming into that positive terminal. So we put on the right-hand side. So this equation has to be true. It has to hold. So that's a complex power balance law. Or if you're not sure which branch really behave as load source, because here it can be more complex because each complex power has real part, imaginary part. Real part is IT power. Imaginary part can be a reactive power. So which means some equipment may behave as active load but the reactive source, or active source but the reactive load. Okay, so if that sounds very complex to you, we can try the different way. We just treat everything to be the source. If you treat everything to be the source, you still need to determine which side has positive terminal, has higher voltage potential. So you always use the current leaving the positive terminal to calculate each individual complex power, which means if we treat, for example, this branch as a source, we should not use this current. We need to use the current leaving from positive terminal, which is negative I3. Then you use negative I3, the conjugated negative I3 multiplied by the voltage, and so that will give you the complex power for this branch behave as source. So equivalently, you can treat everything to be a load, then the current need to come into the positive terminal. So either way, so the equation has to hold. Okay, so next we want to apply this complex power balance principle to calculate power flow for this single very simple circuit. In the session 6, when we talk about power flow analysis, we'll revisit this circuit, but in a more general setup. But here we have to make some very strong assumption, just to make calculation easier. Here we only utilize the definition of complex power and also complex power balance principle to finish calculation. Right? We haven't looked into how to calculate the more accurate complex power for any line in the general conditions. So here, the strong assumption we made include, first we assume the voltage everywhere to be safe. So that can be a fair assumption because in high voltage backbone transmission system, usually we want to maintain the voltage around the nominal value. So the error usually should be less than 5%. The higher the voltage, the closer to the nominal value we want. Okay. So for example, for 500 kV line, usually we want the voltage to be very close to the nominal value. So this is not too bad. So the error could be maybe 5% error. And also we assume all the lines to be lossless, which means there's no resistance. So for any line, the resistance is 0. So only have reactance. Okay, only reactance is not 0. But the reactance can be positive or negative, depending on the line to be an inductive capacitor. But usually, most of realistic transmission line will be inductive line. We'll also prove this one later in the section of line parameter. Okay, so we'll use those two assumptions and to finish calculation. So we want to solve the line flow of every single line. So you see here, we gave some information already. So we usually draw this bar like that one, we call it a bus. A bus means just a substation. So substation can be connected to many transmission lines, many devices. So in the graph, it can be treated as node, but usually in power system, we call it a bus. And so the bus number 1, number 2 will be a power plant. So because they have generator connected to the bus, and those two generators will generate the compressed power. And the bus number 1, number 2 also have a load, a local load, which is SL1 and SL2. Okay, and there's a line connecting bus 1 to 2, and there must be some current, and we just assume this to be the positive current for I12. And substation number 3, the bus 3 also has generator, but we don't know the generation of that generator. And they also connected to a capacitor. So this capacitor will inject some compressed power because capacitor only doesn't have a real power. So the injection will be just a reactive power. So this compressed power only have imaginary power, no real power. We also gave the line flow of the first line leaving from bus 1. Then we need to solve all the line flow, all the other line flow. So even for the line connecting bus 1 to 2, and we want to calculate the compressed power leaving the bus 2. Okay, so you may wonder the compressed power, because this is just single line, compressed power come from bus 1, and is it the same as the compressed power at bus 2? Maybe not, because the transmission line itself is equipment. So you also have some reactance. So we need to utilize compressed power balance principle to finish calculation. Okay. First thing we want to figure out, maybe there's some formula we can utilize. So if we know the compressed power from bus I to bus J, so we use two subscript ij indicating from I to J. So there's also compressed power from bus J to bus I, which those two basically are symmetric about the line, leaving either terminal. Is there any simple relationship from Sij and Sji? They may not be equal and they may not be opposite to each other, but there could be some very simple relationship. If we figure out that relationship, we can calculate this one, right? And based on the power balance, we can calculate this one, and we'll have that one, and this one and that one. So we can make calculation easier. So let's first do that. So by definition, Sij will be Vi multiplied by conjugated Ij, which is the current leaving bus I. And Sji is actually, we use the voltage Vj multiplied by Iji star. We know the I12 is negative I21, right? So current, if we swap the subscripts, and the current has to be opposite. Which means the Sji, if we utilize the Ij, will be negative Vji times Iij star. Okay, so immediately we can get this relationship if we get the absolute value for both sides. So we'll have those formulas. So the absolute Sij will be equal to the absolute Sji. Then from the condition, we know the voltage has same magnitude everywhere. So those two have to be equal. Then which means the two apparent powers measured at both terminals have to be equal. So each apparent power will be can be calculated based on the Pythagorean theorem. So which means this one has to hold. So to continue, next we want to apply the complex power balance to the line 1, 2. So we treat this line as the equipment. Okay. So we want to calculate the power injected into this line and also the power consumed by the line. So basically, we treat the complex power of the line as a load. We put on the right-hand side, and the complex power sent into the line will be the source on the left-hand side. So the complex power into the line will be two items, right? From the left terminal and from the right terminal. So it will be Sij plus Sji. And the complex power consumed by the line will be the voltage drop along the line multiplied by the current of the line and star. Okay, so we know this line is lossless, which means it can be, the reactance will basically just J omega L. So we use another formula. Remember how we calculate the power of impedance. So we use, if we know the reactance, so we'll use this formula to calculate. So the complete formula is the impedance multiplied by the current, absolute current squared, right? But here the R is 0. So the total load will be this one. So to continue, okay. And we know so this formula also tells that the line doesn't consume any active power. There's no active power going to the line because this is completely imaginary, which means if two complex power both come into the line, the real part have to cancel each other. So the active power from the bus 1, active power from bus 2, they have to be opposite. So they will cancel. So 0 indicates this one doesn't consume any active power. And the reactive power together will support this the load of the line. Okay, then start from here. So we know so the Pij plus Pgi equals 0, which means Pij and Pgi are opposite to each other. So the square means this item equals to that item. And also those two together support this one, which means Qij and Qji each is equal to half of this one. So this is a critical step to continue. Okay, let me say that again. So we have to start from there, which is equal apparent power. And because the complex power of the line only have imaginary part, so real part has to be 0, which means active power coming from the bus 1, bus 2, total is 0, which means they are opposite to each other. So if a complex active power starting from bus 1 is, let's say, 100 megawatt, and active power from bus 2 will be negative 100 megawatt. So they have to opposite to each other, such as the line itself doesn't consume any real power. Then we just take those two will be equal, which means Qij, Qji also, the square also equal. So which means they have to be same. Each one will take half of the load of the line. So we'll have this conclusion. So we have those two opposite and those two equal, and each of it will have to be contribute half of the load of the line. So which is like the line itself as a relative load, and the bus 1 will support half of the line, and the other half of the line will support by the second bus. Okay, so immediately we can have this equation. So PJI plus JQJI, which is compressed power on bus 2, equals to PIJ and QIJ are real and relative power from bus 1, from bus I. So to get compressed power of bus J, the second bus, we only just need to add negative sign to the relative power of the first bus, and also we keep the same relative power of the first bus. So which means if we know the compressed power of the first bus, which is bus I, we just put calculate the conjugate and also add negative sign. So we'll have the compressed power of the second bus. This is this conclusion is true for a lossless line with both terminals at same voltage level. At the end of this lecture, we'll go to a more general case. In that case, the voltage are not necessarily same, and also the line has some resistance. But we'll see this formula is still good. It's still very approximate, even it's not accurate. So next, we're ready to continue the calculation for the power flow. Okay, so we start from here, and because we already know S12, and we can calculate S21. Because S12 is 0.5 plus J times 0.2, so we will add negative sign to P, and we keep the same value of Q. Okay, so next we apply the compressed power balance to each bus. We have 3 buses. So bus 1, we have 1 source and 3 load, right? So we have 3 arrow leaving the bus 1. So those will be the 3. And bus 2, we have also 3 load. And for bus 3, we have 2 sources. One is the generator. The other is this capacitor. The capacitor also inject compressed power, even it doesn't have real power. So, but it's still a source. And load only 2. There's no local load, but there are 2 line flows, so which are the load of the bus. So next, we just need to utilize the compressed power balance to each bus. And we start from bus 1 because we start from bus 1 because only the line flow from 1 to 3 is unknown. So only this one is unknown. Anything else already known. So we'll have this one, and we calculate S13. So immediately we can get S31, which will just change the first the real value by add a negative sign, and we keep the imaginary value same. Then we can calculate for the bus 2. So bus 2, we only don't know this one, right? We already we calculate S23, and we already know anything else. So we'll the S23 will be a negative 0.7. So which means S32 will be also negative J0.7 because it doesn't have real part. And finally, we'll do the calculation for bus 3. Okay, so it's done. So we first prove this equation, then we apply this equation together with compressed power balance to finish calculation of power flow. So in the section number 6, we'll work on similar system, but it's in more general conditions. So we'll have both resistance and readings in each line, and the voltage may be different. Okay, so next I want to talk about the concept which is power flow correction. The power flow is defined to be the ratio of the real power to apparent power, right? Because real power is equal to apparent power multiplied by the power factor. And the power factor, because it is value of cosine theta, it will be always less or equal to 1. But if we can make power factor to be very close to 1, we fully utilize this apparent power to become a real power. But if your power factor is bad, which means very low, much lower than 1, you only utilize a certain percentage of apparent power to deliver IT power, which is energy. So when the power factor is low, and if we still want to deliver the same amount of IT power as apparent power, the only thing you need to do, you need to increase the current. So if you have a low power factor, but you still want to fully utilize the capacity or reach the same level of apparent power, you need to increase current by this ratio. So that's why usually we expect power factor to be close to 1. Major load of a power system should have power factor close to 1. That is not a problem for residential or small commercial customers, because most of such customers utilize IT power. They don't consume much IT power. For instance, the lighting load is basically can be modeled as close to a resistor. A resistor may have just IT power. Even it may have some IT power, it could be small. But for industrial load, they usually have motors in the load. So the motor will have low power factor. So to improve their power factor, usually large industrial load need to install capacitor bank or capacitor next to the load. So such as you have overall power factor still be close to 1. So here is a photo of a capacitor bank at high voltage, for instance, 150 kV. The maximal rated power this bank can provide to the system is 75 megawatt. So let's use one example to explain how to correct power factor. So we have a 200 volt AC source supporting 2 loads, and the first one is a purely resistive load, and second has resistance and also reactance. So you will see the power factor will not be 1 because this reactance. And the question first, we want to calculate PQ, basically the compressed power, current, and power factor at the source. Then, based on the compressed power, we can know the power factor. And for this case, the power factor will be bad. And we want to improve the load power factor to 0.8 lagging. So even 0.8 is not good. In reality, most of the load should have overall power factor usually higher than 0.9. So in order to improve the power factor, we want to add this capacitor as a parallel, another third parallel branch connected to the existing load, such that the overall power factor will be 0.8. Okay. So you can imagine without adding this capacitor, there's a theta, which is power factor angle. But adding this capacitor, the overall load will have the new theta. Oh, sorry. We'll have a new theta. We call it a theta prime. So let's see how we are going to address this problem. First, we calculate compressed power for each branch. We use the voltage, absolute voltage squared divided by the Z star. You use this formula, so we can get the load 1 has no reactive power. The load 2 has both reactive and reactive power. So total load will have 1200 P and 1600 as Q. So please memorize this triangle. So that will be very convenient, because in the homework and test, I'll try to use this formula to make calculation easier, right? This angle is, what is this angle? Usually this angle is 36.9 degree, right? This angle is about 53.1 degree. That just memory the triangle. So for this case, we have 1200 and 1600, which is the ratio of 3 to 4. So the angle has to be 53.1 degree. Current will be the compressed power divided by voltage, then calculate the conjugate. So that will be 10 and a negative 53.1 degree. So negative 51.3 degree means the current is lagging the voltage by around 50 degree. So that's why there's a negative sign. Power factor will be just cosine 53.13 degree. So that's 0.6. So it's very bad, right? It's a much lower than our goal. Our goal is 0.8. Okay, so if we use a phasor diagram in the complex plane, the x, so this is the real axis, and this is imaginary axis to calculate to show the complex power. So this is a P, 1200, right? And this is Y, the OQ, 1600, and the total angle is 53.1 degree. And that will be a 0.8 lagging power factor. And we want to improve the power factor 0.8, so which will make this angle be smaller, such as this divided by that part become 0.8. Okay. Then we'll need to have a new reactive power injected to the system to compensate part of the inductive load, the reactive load, by this inductor. Then such as finally, the overall reactive power is smaller. And that improve the power factor angle to make it smaller. So based on the new power factor 0.8, we can also utilize that triangle. So the angle will be a 36.9 degree. So the new reactive power, this Q prime, which is overall reactive power of the three branches together, will be because we keep the P unchanged. So using the new power factor, the Q will be 900. So this part will become 900. So we'll decrease from 1600 to 900. From 900, and we know the QC will be a negative 700 bar. So in the slides, I ignore some details, but I will just make up that details to make it clear. So the QC will be a negative 700 bar, which means it will be a reactive source. So using this Q, and we can calculate the impedance of the capacitor. So impedance of the capacitor is defined to be 1 over j omega c. So if we know the capacitance, so this will be the impedance. So impedance is equal to absolute voltage squared divided by the conjugated value of the complex power, right? So this is the formula. So here we utilize the formula. So if we know the voltage, we know the complex power of the element, so we can use this one. This is also the same formula. If we know the voltage, we know the impedance. So those just equivalent to each other. So first one, if no voltage and no complex power, this is the impedance of the element. Oh, voltage, impedance, we can calculate complex power. So that's this formula. So JC will be negative J57. The negative sign indicated is a reactive, capacitive load. And C will be around 46 mu F. Using this added capacitor, finally the total complex power will be 1200 plus J 900. So you see the first real part doesn't change at all, but the imaginary part becomes smaller, and angle become around 36.9 degree, and the magnitude is changed from 2000 to 1500. So apparent power decreased, but active power is same. The new current is also smaller compared to original current 10. So by improving this power factor, by adding the capacitor, and we can reduce the current by 25% without changing any real power. Okay. So that's the benefit of correcting the power factor. Any question? There's also another example, 2.4, but on a similar circuit with high voltage setup. I upload the toolbars attached with the book, so you can easily find. There's a MATLAB code, probably maybe ESP 2.3 or 2.3, something like that. So you can find that MATLAB code. So if you run the code, it will give you the exactly same result, but you can play with the code. For instance, what if you improve the power factor to 0.9, okay, or even to 1? 1 means this complete compensation. So you have a capacitor fully compensate the reactive power of that inductive part. Yeah, so you can try that to see what changed. Okay. All right, next we want to find like more general formula for this one, right? Later, using that example, we have this approximate formula. To use that formula, we can calculate condensed power from one side to the other side. But that is based on two assumptions. The first, voltage are same. Voltage will have the same magnitude, and also transmission line doesn't have resistance. But right now, we will work on a more general case. So we do need to consider resistance R. And also, we don't know really that the two voltages will have exactly same absolute value. So let's work on this more general case. So now the each voltage, the impedance and the power will be all complex number. So we need to deal with calculation using those complex number. So I assume the bus 1 will have this magnitude, this angle. Bus 2 have this magnitude angle, and also impedance have a magnitude angle. The gamma just the angle of the impedance. To calculate the current, I12 is current leaving from bus 1 to bus 2. So that current will be just the voltage drop divided by impedance. So we just plug in those complex numbers in their phasor representation. And so to calculate this one, we just divide the magnitude of the numerator by denominator, right? And angle will be a subtraction. So it'll be the angle on the top minus the angle on the bottom. So next we calculate complex power. So we use the voltage on bus 1 multiplied by the conjugated value of the current leaving bus 1. So will be this current, we calculate the conjugated value, then multiply the V1 by this value. So it will have this expression. Okay. So next we do some simplification. So because outside of the bracket will have a delta 1 and inside we have a negative delta 1. So we can cancel the delta 1 for the first item. The first item will not have delta 1. And the second item, the delta 1 and the negative delta 2 will combine. So we'll have the second item will have gamma delta 1, delta 2. Okay. Similarly, we can get another formula for the bus 2 because we only just need to swap 1 and 2. So here you have 1, 2, and 2, 1, and 1 become 2, right? And the delta 1 minus delta 2 become delta 2 minus delta 1. So those two will be the accurate formula for this one. But it may not be easy to use. And also, we want to prove this one is similar to that one, but it will give you better accuracy. So we want to translate the complex power into active and reactive power. Then we will consider some typical condition. So if we take a real part, we simply just have this one anywhere we see angle. You see angle, you see gamma or this angle, everywhere with angle, you just replace by cosine value of that angle. Okay, so this will P, and Q will just change that one to a sine angle. So we have a P and Q. Similarly for the S21, we will, before that, let's consider a similar case. Let's just assume R to be 0, which is lossless line. That will make the impedance will be equal to the reactance. And the gamma, which is the angle of impedance, will be 90 degrees. Okay, so what will change? So each absolute Z will become X. Gamma will become 90 degrees. Do you know what cosine 90 degree plus certain angle become? Will become something like a sine this angle, right? If you remember formula. If you don't remember formula, don't worry. You just need to draw the circle, draw the unit circle, and just make sure the sign will be same. So you know anywhere here, if you have 90 degree, if you get rid of that 90 degree, you switch between cosine sine, but make sure the value will be same, will be not opposite. You just plug in, maybe just give this angle some very easy value, like 45 degree or 30 degree. Just make sure that the two answers have both positive and negative. So I will just give you the result. So this will be the active power and reactive power. And the first item is gone because cosine 90 degree is 0. But compressed power is still maintain the first item. So here the sine angle become cosine. Okay. Those two will be the more accurate formula compared to this proximate one. Similarly, we can get active power sent from the right-hand side. We only just need to swap 1 and 2, right? And then this one will be negative P12. So this conclusion is the same as that proximate formula. Remember, we have the P12 and P21 to be opposite. The Q will have this formula, will be this one. Okay, so next, let's just give the circuit some value so you can have better idea on how the compressed power can change along this transmission line. So we assume the first bus have voltage magnitude 120 and has negative 5 degree, very close to the angle of the second bus. For second bus, we treat that one as reference. So voltage 100. So that we intentionally make bus 1 to be slightly higher, 20% higher than the bus 2, and angle to be slightly lower than the bus 2. And for the impedance, we have both R and X, but we intentionally make R to be much smaller than X, right? So which means this line is still, it's not lossless, but the loss is still it's not a major part of the line. So we want to utilize the formulas from previous slides. For current, you just plug in the V1, V2, and Z. You can finally, after simplification, you can get this current. And for I21, which is simply just opposite I12, so it will be this angle. So basically have the same absolute value. Angle will be, you add 180 degree to the angle. So it's just opposite to each other in the compressed plane. Then calculate S12 and S21. You just use the formula from previous slide, and then you can get two compressed number. And if you write each one into the real part and the imaginary part, that will tell you the active power and reactive power. So the active power from bus 1 will be negative 97.5. Okay. The active power from bus 2 will be 100 over 107.3. So what does this one mean? So first, the value of the magnitude very close. And this is negative, this is positive, which means active power is coming from bus 2 to bus 1. Because here, whatever leaving, the active power leaving bus 2 is 107. And whatever leaving 1 is 97, which means coming to 1 is 97. So the gap, if you ignore the negative sign, the gap will be about 10. The 10 watt will be lost along the line due to that resistance. Okay, that's the real power. For the reactive power, the bus 1 will send 363 reactive power to the bus 2. And the bus 2 will send negative 294, which is also negative, which means they will receive 294, right? The difference, which is about 70 watt, will be whatever loss along the line. What is the load of the line? The load of the line will be the loss for this part and also loss for that part. So that confirm will be 9.8 watt loss as active power and around 70 watt loss as reactive power. Okay, so that maintain the complex power balance. Yeah, so you can use this formula. You treat S12, S21 to be the source and this one to be load. It will give you exactly the same answer. So the first one, just use the current and line impedance to calculate the power, and second, just use the complex power balance. So if you visualize how the power is sent from one end to the other end and also consumed by the line, we can draw those green arrows start from bus 2. So you have 107, then 9.8 will be lost by the line. And then to bus 1, you only have 97.5. Reactive power is coming from bus 1, so you start from 363, and at the end you get 294, and this part will be the loss. Any question? Everybody has followed? Okay. Let's move on. Okay, we try to generalize this case to see how the angle can change if we vary the bus 1. Okay, so remember at the beginning, we intentionally make this angle to be very close to this angle. But what if we make the range of change to be bigger? So we allow the angle of a bus 1 to vary between negative 30 degree and positive 30 degree, give a bigger range to vary to see how the complex power flow can change, maybe can reverse direction. So we can draw this figure. So what you can do the same thing to easily generate this figure by going to that example. So in that example, you set up the angle, I start from 95, right? You can change this value to play with this value to make it be any value in that bigger range. And for each value, you can calculate the power flow, and then you can draw this figure. So this figure tell, okay, so when the angle vary from negative 30 degree to 30 degree, the P12 is actually the active power from bus 1. So this one will start from a negative value, will increase to a positive value. So when delta 1 is higher than the angle on the bus 2, so eventually the active power will become a positive. But if delta 1 is lower than the delta 2, the active power will become negative. So at a certain point near 0, which is about the same angle of that one, so the active power will become about 0. So in the AC circuit, the active power direction depends on which side has higher angle. That is very important. It's very different from DC circuit. In DC circuit, which side has higher voltage, that will be the power coming from. But in the AC circuit, you need to have higher angle in order to make that terminal to be a source, right? So the active power from the bus 2 will be opposite, almost like symmetric about the IT power from bus 1. And this line indicates the loss, how the loss change. You see, it's almost flat, but at some middle point that has lowest loss when the two terminal has similar angle. So if we zoom in for that rectangular area, which will be this one, so we will focus on the change of the delta 1 from -5 to 0. So there's some point the P12 is equal to P21. So they both positive, both slightly higher than 0. Okay, so when the angle is around 95 degrees, so this is 0, this is around 95 degrees. If you measure IT power from both terminals, they're exactly the same and slightly higher than 0. So what does that mean? What does that mean? Because this line is not the lossless line. The line will consume some IT power. So both terminals will contribute a little IT power as much as this amount to compensate the loss of the line. Okay. If the line is lossless, this value will be exactly 0. Okay. Okay, so we want to come back to a lossless line because that's the easiest case. So for lossless line, R is simply just 0. And we start from those two formulas, and we'll know for lossless line, we'll have those two formulas. And if we assume also P1 is equal to P2 in terms of absolute value, so we'll have the both Q to be same. So that will go back to the original approximate formula, right? We assume at the beginning. So if the angle difference is small, let's say less than 15 degrees, sine angle will be roughly that angle. So cosine angle will be roughly 1. So we can further simplify the formula into the following one. So power will be, IT power will be proportional to the angle difference. So direction of IT real power flow really depend on the angle difference, which side has higher angle. So if voltage 1 is leading voltage 2, and the power flow will be from bus 1 to bus 2. So the theoretical limit will be this one, when this angle take a 90 degree. So that will be the limit of the IT power. For the IT power, that depends on which side has higher voltage. So IT power is sent from the high voltage terminal to low voltage terminal. Okay. We will come back to this one on Monday, so with some more practical application of those conclusions in real power system.